Welcome to Part 2 of the COVID spread model. In Part 1 we considered a nursing home. We built a model in which one individual contracted the disease. We predicted how the virus would spread from that individual to others within the institution. Eventually the disease would die out as the recoveries outpace new infections. This occurred because we imposed the restriction that a recovered individual could not become reinfected. Given documented cases of reinfection following recovery, we need to build this possibility into our model. That model, you may recall, was embodied in these three equations. Think of all the values of S, I, and R over all the time points. Imagine that these numbers are stored in a table. That table is a two-dimensional array having three columns. One column for the number of susceptibles at each time point, one for the infecteds, and one for the recovereds, and a row representing each time point. We'll call this array U. We can address any cell in the array by its row number and column number. These are its indices. Both row and column indices start their numbering at 0. For example, the value of S at time point 0 is referenced by U brackets enclosing the row number 0 as the first index, comma, and the column number 0 as the second index. As a second example, the infecteds at time point 2 is referenced by U2, 1. Now that we understand how to refer to any cell in the array, let's define a function we'll call f. Line 1 declares the function. The code that calls this function passes to it U, which will be a row from our array U, and T, which will be the row's time point. In the next line, we assign to S, I, and R, respectively, the three values in U at the current time point. And in line 3, we return to the calling program a list of the results of the three computations. We see that F returns all the information needed to execute our SIR model because the expressions in the returned list minus beta Si minus gamma I, and gamma I are the right-hand sides of the three SIR equations. So we are returning to the calling program the instructions for calculating S, I, and R at a given time point. The calling program is our generic solver. What does this solver program look like? Well, here it is. In lines 1 and 2, we import NumPy and pyplot as we did in part 1. Line 4 declares a function we'll call ODE_FE. ODE stands for Ordinary Differential Equations, and FE refers to the forward Euler scheme, which is a numerical method for solving ordinary differential equations. We see in the function's parentheses that four entities or objects are passed to it. The first is F, which we know will give it that list of results of those three computations. Besides F, the other parameters expected by ODE_FE will be the starting conditions passed as an array U_0 of three values which are the initial states of S, I, and R at time point 0. Our time interval is dt, and the total time period, uppercase T, we want to cover. Line 5 assigns to n_t the number of time points. It will be the rounded result of dividing the time range, uppercase T, by the interval dt, and we convert the result of that to an integer. Line 7 uses Python's lambda function to pass u and t to NumPy function as array. As array converts, or we can say wraps, the list of values returned by our function f in an array easily manipulated in NumPy. Line 8 creates a two-dimensional array u containing all 0 values. We pass to the zeros function two indices defining the shape of the desired array. That shape will be n_t plus 1 rows, that is, the number of time points to be covered, and the number of columns, which will be the length of our initial condition vector u_0. In our case, that length will be 3, given that we have 3 initial conditions, s at 0, I at 0, and r at 0. The zeros function has two sets of parentheses. The inner set is simply the syntax for designating an array. The outer set is the required form of a function. Line 9 sets up t to be our array of time points. Line 10 sets the 3 starting points for the model's computation. Line 11 and 12 is our for loop that will repeatedly compute the values of s, I, and r at upcoming time points, n plus 1, given their values at time point n. We recall that in part 1, this loop had 3 lines. But now, using our array u, the computations are carried out with a single compact line of code. The for loop computes and stores in array u the values needed for all 3 plots. In line 13, rather than plotting right away, we'll simply return the complete arrays u and t to the calling code, which will be our implementation code. What does that code look like? Here it is. Our implementation code defines the function demo_sir. It doesn't take any parameters, so its parentheses are empty. In lines 3 to 5, we incorporate our f function that returns the results of calculations according to our SIR model. Next, in lines 7 to 13, we provide the specific information describing our particular problem. These include the constants beta, gamma, and delta t, our initial condition list, u_0, our time horizon, d, of 30 days, the number of time points, n_t, and our time range, uppercase T. In the single line 15, we call our generic solver, ODE_E_FE, sending it the f it will use to implement our SIR model, the initial conditions, the time interval, and the time range, everything it needs to compute and send back the arrays u and t that will be used for plotting. In lines 17 to 24, we perform the plotting. Lines 17 to 19 assigns the arrays for S, I, and R as u followed by brackets. The first index for all 3 is a colon. This tells the plot function to include all the rows in the array, that is, all the time points. The second index is 0, 1, and 2, which picks out the values respectively in the columns S, I, and R at each time point. Lines 20 to 24 execute the plot exactly as in part 1. Now, in lines 27 to 33, we add something new, a consistency or sanity check. Obviously, the 3 values at every time point must add up to their sum at time 0. That sum was assigned to uppercase N in line 27. In other words, no individual within our closed system can escape the accounting process. Line 28 assigns to variable EPS a tolerance of 10 to the minus 12. This will be used in our test for consistency. Line 29 begins the for loop over the range of time points, which we provide as the length or number of rows in our susceptibles array. Line 30 computes the sum at each time point n. Line 31 performs the test by making sure that the difference between the true n and the calculated sum does not exceed the tolerance EPS. If it does, it prints out text stating that the check failed and prints the offending sum and the target n. We use the tolerance rather than simply testing whether our count equals n because that will never be precisely true due to the way real numbers are stored in a computer. Finally, in line 35 and 36, we run our demo SIR function. The syntax, if name equals name, is a Python technique to tell our programming environment that we are executing demo_SIR directly from this program. Otherwise, if the function were being called from another program, the code in this if statement would be ignored. Okay, let's run this. Sure enough, we get our expected plots identical to those of part 1. Now that we've seen how to use a two-dimensional array to represent all the computed values of S, I, and R, we can easily expand the model to cover the possibility of limited immunity, meaning that some recovered individuals can be reinfected. Modeling the loss of immunity is similar to how we modeled recovery. The amount of people losing immunity will be proportional to the amount of recovered patients R and the time interval delta t. We'll call the proportionality constant the Greek letter nu. Nu is the probability of an individual losing immunity in a unit of time. So we can write the loss in the R category in time delta t as minus nu delta t R. Nu would have been determined by observation in comparable environments. The loss in R, of course, is a gain in S. This is our revised SIR model incorporating limited immunity of recovered individuals. Now we'll bring back our implementation program and make some simple changes to accommodate this updated model. Let's add a note to our functions doctext that we are including the possibility of limited immunity. In the list returned to our generic solver program, we subtract our loss factor, nu times R, from our recovereds, and we add the same factor to our susceptibles. Next, we'll adjust beta to 1/4 its original value. This lower infection probability will allow more time for loss of immunity to be observed. We print that value so that we can play with it and assess its effect. No change in gamma, or the time interval dt. We'll increase our time range to 300 days to give us sufficient time to observe the new behaviors of S, I, and R. The other constants are unchanged, except that we add a value for nu, which is the expected reinfection rate. 1 out of 24 recovereds were observed to have been reinfected in a 50-day period. The rest of the program is unchanged. Let's run it to see our new plots. Having reduced beta and set mu, we see an oscillatory behavior in the categories. This graphically depicts the appearance of embers or hotspots referred to by President Trump and Dr. Birx. It is easy to play around and study how the parameters affect the spreading of the disease. For example, making the disease slightly more infectious by increasing beta to 0.00043 lead to more pronounced embers. We should extend the model to include the effects of vaccination. To this end, it can be useful to track people who have been vaccinated and those who have not. So, we introduce a fourth category, V, for those who have been successfully vaccinated. A percentage P of the S category will be vaccinated in a unit of time. This means that in the time interval delta t, P delta TS people leave the S category and enter the V category. The extended model adds a fourth difference equation. We've assumed that vaccinated individuals cannot get the disease. If the vaccine were less than 100% effective, we could subtract an expression from the V difference equation and add that same expression back to the S equation. Such an expression would model the reduced effectiveness of the vaccine. But for now, let's make the code changes assuming a 100% effective vaccine. We'll revise our functions docstring to indicate limited immunity as well as a fully effective vaccine. We'll modify the list returned to our solver program so as to include the right-hand side of our fourth, that is, our vaccination equation, by adding P times S, which counts the number of people vaccinated in time interval delta t. And we subtract that same term from our S expression. We'll add a starting value of 0 vaccinated at time 0 to our initial condition list. And we'll set our vaccination rate, P, to 5 in 10,000 in a unit of time, and print it in case we want to adjust this policy later on. The rest of the program remains unchanged except for adding vaccination terms where needed in the code. Run the program. Now we have 4 plots. The V plot predicts 43 of the individuals will have been successfully vaccinated during the course of the pandemic. There's a peak indicated of only 7 infecteds, which would occur at about 500 hours or 20 days. And no new embers or oscillations are seen after that. It looks like the vaccination program should be effective in the initial spread of the infection and also in preventing recurrence of hotspots. Let's run this one more time, but this time we'll cut down our policy vaccination rate from 5 in 10,000 to 1 in 10,000 in a unit of time. We see that the embers are back. I hope this has provided some insight on how models can assist in setting policies to maximum effect. Thanks for watching.